Yeah, just as before, we add a half wave every single time. Third harmonic. Then, how many waves? Yep. It depends upon your family. Fractions, decimals, mixed numbers. So something that has two free ends, we would actually, it's a little bit difficult to conceive of, for at least for me until I actually saw it. This has two free ends. Both ends are open. If I swing it with the right frequency, I can produce sound. That's a harmonic. That's a harmonic. Those are all harmonics. And we can predict what those frequencies are going to be. Now, having gone through this, that first harmonic that you actually hear is the second harmonic, not the first. You can't hear the first one. As I swing this around, the end out here obviously is moving faster than the end down here. Since this end is moving faster, there's a lower pressure here than there is at this end. That difference in pressure means air is going to be pushed up through the tube this way. The ribbing makes the air start to vibrate, and we get the harmonics. For the first harmonic, I'm swinging it so slowly, there's not enough pressure difference to get air to go really through it of any significance. Unless you potentially really good hearing. Can you hear that first harmonic there? That's the second harmonic there. Second. And so, let's suppose we make our prediction, and we're trying to figure out, is it the same? Well, let's first make our prediction, and then we'll figure out how good your hearing is. Occasionally, I do have people with musical training or just naturally can hear some differences in frequency. I cannot. I have to go to a different means. The first harmonic is a half of a wave. L is the length. It is the length of the tube. Just measuring that length. I'm going to stretch it some because as I swing it, it will stretch some. We'll also want to make it straight. I'm getting about 86 centimeters or 0.86 meters. The first harmonic. My wavelength L is a half of a wave. So the wavelength is 2 times L, or 1.72 meters. If I doubled that correctly. Now the speed of the air going through the tube, at least the part making sound, is the speed of sound. I know that the speed is the frequency times the wavelength. The speed of sound in this room right now is roughly 340 meters per second. And that's going to be equal to the frequency times the wavelength, 1.72 meters. And while someone is figuring that out, we'll see if I can get in quickly enough so you know what it's supposed to sound like. All right, so what is the frequency of the first harmonic?
197.67.
197.67. In order for there to be sound, I have to do this. All right. The LabQuest will also do it, but they don't do fractions. So move down here, 197.3.
6, 7.
So this is what it sounds like. Yeah, there we go. Nailed it. All right, second harmonic. Second harmonic, L is the wavelength, so the wavelength is for the full thing. So for the second harmonic, L is going to be 0.86 meters. And so 340 meters per second, my speed, is equal to my frequency. I'm going to put an f sub 2 there, f sub 1, second harmonic, times 0.86 meters. And so the second harmonic units off there. Somebody should have said something. So 395.35. Okay. It's a different timbre, however it's supposed to be pronounced. The fact that they're two different materials, so there's going to be some inherent differences in the sound. It's a matter of how close are the frequencies. So how can you figure out how close frequencies are? What I did is I took two patterns here. So this has a certain frequency. Hopefully you can see the purple lines, or the purple curve. And not that one, not that one. There we go. And this is blue. So they are two different ones. They are slightly off. If it looks like they are the same, if you look, they both start at the same place, but this one ends on the way down. This one ends after it's already bottomed out and it's coming straight back up. But they are very close to each other. I then took the blue one and I traced it onto this transparency here. So it should line up. So I trace it onto the transparency. So now if I take the purple one, if I start them in the same spot, get it off there. Start them in the same spot, hopefully that you can see that they start to get out of sync. Here they look pretty much in sync, definitely some constructive interference going on, but as we get further out, by this point, they're peaking in different spots. And I'm assuming that all of you have such incredible eyesight, you can see that. Now, what does that sound like, if this were sound? Well, if you add them together, you get this, usually without the water spot. It starts out with a peak somewhere around 2, but then notice that the peak gets smaller and smaller. If I extend it out, it looks like this. So if this were sound, this would be the loudest sound, and this would be silence. So if I played I don't know why I thought it would just instantly appear. All right, so if I play 440, so that was 440, and now let me get past pass the ads. 439. How many of you could hear the difference? I know there's some people who can, but 440, 439. Now, for some of us, I can't hear the difference, so let me play them at the same time. Now, the wah-wah sound has its own frequency. So let's get into the sophisticated math of that. Prepare yourself for the most sophisticated math possible. To find the beat frequency, I take my two frequencies here, 440 hertz and 439 hertz. Here we go. Subtract 1 hertz. That is the beat frequency. So the wah-wah sound should happen every second. Let's see if that plays out. Or let's take it that next step, in this case. I know that the frequency is 1 over the period. If the frequency is 1, that's 1 over the period. Doing the fancy math, t is equal to 1 second. Wrong one. That's 439, 440, 1001, 1001, 1001, 1001. If I did 4039.5, I'd have 440 minus 439.5 would give me 0.5 hertz is the frequency. The period is 1 over that. And what's 1 divided by 0.5? So we should be 2 seconds. And with the little time remaining, as you get older, this is a little pro tip for your kids if they're annoying you. I can't hear the following frequency. How many of you can hear that? Yeah. Probably the pettiest thing I did when I was over in Ardmore and students were being too loud outside my office. I'd crank this up and entertain myself, and they go, "Does anyone else hear that sound?" I didn't think about it until I did it by accident in class. But anyway, hopefully you're not hearing it now. See you tomorrow. The lab is posted and I believe visible. I think I got that.